Good afternoon. I am Hunter Ferguson presenting chlorine fluoride versus chlorine trifluoride. Now this is over our group 1 project. Me and Lauren Singer put this together. So I'm going to go ahead and knock this out real quick because I am running out of time. So we got our Lewis structure. Lewis structure for ClF. ClF. Now 14 total valence electrons because there's 2 halogens. 2 halogens means that there are 7 valence electrons each. Sorry, I just don't like the way that looks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, boom, easy, right? Now let's go ahead and double check the formal charge here. So chlorine has 7 total, so we're gonna go ahead and subtract the 1/2 of the 2 minus the 6 equals 0. Same thing for the fluorine, 7 minus 1/2 of 2 minus 6 equals 0. Now, easy enough. Formal charge 0, good deal. Now let's check out resonance structures. Only one bond. Really hard to have a resonance structure when you only got one bond. So therefore, not an issue. Now, polarity. Polarity is pretty easy to calculate when it comes down to this. So polarity is electronegativity, essentially. So Cl is 3.2 electronegative and fluorine is 4.0. That means that fluorine is 0.8 more electronegative than chlorine. So we can put a sign here, boom, boom. Easy, right? Maybe too easy. Essentially, what that means is that fluorine is getting the polarity. Therefore, are getting more electrons, polarity, etc., etc. Not too worried about it. But definition of polarity based off of that is 0.4 over here, right? Anything below 0.4 is considered a pure covalent bond. Anything between 0.4 and 1.8 is considered a polar covalent bond, and above 1.8 is going to be an ionic bond. Easy enough, right? Now let's go ahead and check with our rules. Do we break any rules with this structure? Nope, we do not. Hybrid orbital, not too worried about that right now. But let's take a quick look at what we have here. So what we have is we have a single bond connecting chlorine and fluoride. Now, the bond strength between chlorine and fluoride is going to be 253 kilojoules of energy per mole. Therefore, it's pretty low. Therefore, it's going to have a pretty low boiling and melting point, which can be seen here. Our melting point of chlorine fluoride is going to be 117 Kelvin, extremely low. And our boiling point is 173 Kelvin, meaning that minus at negative 100 degrees Celsius, it is still a gas. So, extremely, extremely volatile, because that's what volatile means. Now, it is a gas or gaseous at room temperature. It's odorless, easy enough, right? And then also it reacts with organic material. So when I say that, I mean it essentially, if you breathe it in, it's going to affect your lungs, it's going to affect your eyes, and if you somehow get it on your skin, it's going to burn your skin. So it's very, very, very reactive with organic material because, well, that's what we like. Anyways, now we covered that, let's cover chlorine trifluoride. Already drew the Lewis structure because I spent way too much time on it last time. So we have chlorine and then 3 fluorides connected with 3 bonds. And then if we look on the outside here, we fill up those outer layers, and then we still have a couple left over, so then we fill up the center layers. Now let's go ahead and do the formal charge, our formal charge, make sure I'm not crazy, make sure I didn't do anything wrong. So let's do fluorine. Fluorine is going to be the same over here as it was, or same as over here, so it's going to be 7 minus 1/2 of 2 minus 6 equals 0, because that's how it works. Now let's check chlorine. So it's going to be 7 minus 1/2 of 6 minus 4 equals, well, that's 3 minus 4 minus 3 minus 4 is 0. So we have a 0 formal charge there. Meaning, you guessed it, that's the correct structure. But Hunter, we have too many electrons. Simple answer. We can break the octet rule every once in a while. Is it good for the good? Not really, but we'll get there. So, when we break the octet rule, what we do is we call, let's call a hybridization of sp3d1 orbital, right? So, that is where we're at right now. So, now that has to do with what's called our molecular geometry, which our molecular geometry for chlorine fluoride, by the way, is going to be linear because it's just a straight line. Pretty boring, actually. But over here, our molecular geometry for chlorine trifluoride. Well, first, let's look at all the electrons we have. We have a group here, a group here, a group here, a group here, and a group here. That means we have 5. 5 groups of electrons means that we are in trigonal bipyramidal. That's not the molecular geometry, that's the electron domain specifically. But what we do is we subtract our non-paired electrons minus our paired electrons. So essentially it's going to be 5, or minus our total amount of electrons, which is going to be 5 minus 2, which gives us what's called a T-shaped molecular geometry. Pretty easy to follow, right? So, it looks something like this. That's more or less what it's going to look like. So, now, resonance structures. Essentially, because we don't have any double bonds here, we don't really have any resonance structures. Sucks. Determining the polarity. Well, an easy way to do that whenever you have multiple bonds like this, especially 5 or more, is typically what you want to do is you want to look for symmetry. So if you flip these over, is it the same? The answer, no. So therefore, we're going to have bonds going this way, this way, this way, this way. Essentially, we're going to have a nonpolar bond. It's most likely going to be going some way this way overall. So that's where we're at. Now, we have a polar bond that broke the octet rule. What does that mean for us? Well, we can go back to the basics. We can look at how many sigma bonds we have. 1, 2, 3. That gives us 759 kilojoules of energy required per mole to destroy it, essentially, right? That means that we're most likely going to have a higher boiling point against this one over here, right? So look at that. Boom. 285 Kelvin and 195 Kelvin for boiling point and melting point. For boiling point, that's only 12 degrees Celsius, which is not that low compared to our previous minus 100. So it's a pretty significant difference there. Now that means that it's not more stable, but it is realistically going to be more active in the environment or able to react in the environment. So we have that. But what is this 493 we have here, right? It's 493 degrees Kelvin. What happens when you heat a molecule to that speed, or that height of temperature? Well, specifically, this molecule begins to decompose. If it is in a container, it may actually explode. So, just a possibility. But, yeah, extremely dangerous. Anyways, enough of that. Let's talk about the physical and chemical properties. We're gaseous, or gaseous, at room temperature with a sweet odor, semi-sweet odor. And then whenever it's liquid, which is typically how it's transported, it's going to be pungent smelling, and it's going to look greenish yellow, which is kind of pungent looking too, if you ask me. It is highly, highly, highly reactive to organic material and other materials as well. So water, for example. If water is mixed with, let's say that we have water vapors and we have the chlorine trifluoride vapors, right? If they mix together, they make a lot of really nasty gases that can actually kill people. So it's a highly, highly, highly reactive element with other materials. It was used in World War II by Germany as a incendiary gas. It's also used as a rocket igniter. So that doesn't give you a good idea. That I don't know what will about how volatile or not volatile, dangerous, hazardous it is. I get those words confused all the time. And then and then nuclear. So it's used also in preparing nuclear material for reactors and stuff. So just an overall, a lot of stuff it's really used for is really good and it's super helpful, but it is also dangerous. So keep that in mind. Yeah. Thank you for listening, and I hope you enjoyed the presentation.